Silica minerals. The Earth's crust is primarily made of 8 elements. The Earth is differentiated into 3 major compositional layers: crust, mantle, and core. Most of these layers is made of just 4 elements: iron, oxygen, silicon, and magnesium, in some kind of combination. Dense metals such as iron and nickel sank to the core during the early history of the planet. The core and mantle do contain silica, but is far greater in quantity in the crust. Analyzing the minerals of a characteristic rock of the Earth's crust show that oxygen and silicon makes up 75% of the elements present. In combination of a handful of other elements, oxygen and silicon combine to form the most common mineral group, the silicates. Silica minerals make up only 26% of the Earth's crust, due to the dominant feldspar family, namely plagioclase and orthoclase feldspars. The silicate family can be broken down into 7 major groups, namely neso or orthosilicates, sorosilicates, cyclosilicates, inosilicates, and tectosilicates. I'm going to focus on tectosilicates, also known as framework silicates. The silica family is part of the tectosilicate group. There are 3 main forms of silica: crystalline, cryptocrystalline, and cryptocrystalline hydros. I'm mainly going to focus on crystalline silicas. Crystalline silicas is simply the crystalline form of silica. Its main varieties is quartz, tridymite, and cristobalite. The chemical composition is relatively simple, as most quartz consists of 99.9% silicon dioxide. Quartz occur in many varieties, in almost all types of igneous, sedimentary, and metamorphic rocks. Quartz crystals lack a center of symmetry or planes of symmetry, and have one crystallographic C-axis, perpendicular to 3 polar A-axes at 120 degrees apart. One end of a polar axis is different from its other end. When mechanical stress is applied on such an axis, opposite electrical charges develop on each end. This leads to important applications in electronics, such as frequency control, pressure gauges, and many more. The lack of symmetry planes parallel to vertical axis allow quartz crystals to occur as 2 types: left-handed or right-handed quartz. This is called enantiomorphism. If polarized light is transmitted by a quartz crystal along the C-axis direction, the plane is rotated in the direction of the handedness by tens of degrees per millimeter. This amount is determined by the wavelength of the transmitted light. The property is used in optical instruments such as monochromators. The electronic frequency applications demanded higher quality crystals. This led to the development of industrial synthesis of silica crystals. Quartz comes in different forms. The ideal crystal shape is a 6-sided prism with 6-sided pyramids at each end. In nature, quartz are often twined, distorted, or so intergrown with adjacent crystals of quartz or other minerals to the point that some appear massive. Colored variations of quartz are numerous and have many causes. These color differentiations arise from presence of impurities which change from molecular orbitals, causing transitions to take place in visible spectrum, causing color variations. Common examples include citrin, that's yellow, rose quartz, amethyst, that's purple, smoky or Morian quartz, that's black, milky quartz, and many more. Quartz can be alpha quartz, that's low temperature quartz, or beta quartz, also known as high temperature quartz. The transition from alpha to beta takes place at around 573 degrees Celsius. There is a lot more polymorphs at higher temperatures and pressures. This leads to the very complicated phase diagram of silicon dioxide as seen on the right. Beta quartz may be either left or right-handed, and its C-axis is one of six-fold symmetry rather than threefold. High quartz can form directly from silicate magma or from high-temperature gases or solutions. It inevitably undergoes a transition to alpha quartz on cooling. The reverse is also true, as alpha quartz is heated to form beta quartz. The transition involves displacement of linkage between the tetrahedrons. Therefore, no bonds are broken. Natural tridymite has no specific commercial use. Tridymite is stable at around 870 to 1470 degrees Celsius at atmospheric pressure. Tridymite can occur as primary magmatic phase in siliceous rock, that is sedimentary rock largely or nearly entirely consisting of silica. Tridymite also forms as contact metamorphosed rock. Tridymite is also very common in cavities of felsic volcanoes, where it probably was deposited metastably from hydrous gases. Tridymite occurs in 7 crystalline forms. The most common at standard pressure is alpha and beta tridymite. Alpha tridymite or high tridymite converts to beta cristobalite at 1470 degrees at atmospheric pressure. Tridymite does not usually form from beta quartz. Trace amount of certain components needs to be added for this to be achieved. Otherwise, cristobalite is directly formed, as the beta quartz tridymite transition is skipped at 1500 degrees at atmospheric pressure. Cristobalite. Cristobalite is more abundant in nature than tridymite. Although it seldom forms as distinctive crystals, siliceous volcanic glasses yield abundant tiny crystallites of cristobalite via differentiation, the transformation from glassy to crystalline state. They are also found in cavities of felsic volcanoes, where it probably was deposited metastably from hydrous gases, just like tridymite. It is also used in dentistry as a component of alginate impression materials, as well as for making models of teeth. The Wikipedia reference refers to the silica table that was used in slide 3. No information or data were used from Wikipedia.